Hi, today we're going to talk about Gandalf, an intelligent end-to-end analysis service for the safe deployment of cloud-scale infrastructure. Brought to you by team number 7, consisting of Mo Girona, Tom Manon, and Dejing Kong.
Okay, for the presentation, I will give a brief introduction and motivation part of the Gandalf. And then my teammates, Thomas and Moise, will provide the details of Gandalf, include the designing and the implementation. So at last, I will do the evaluation and provide some research conclusion. Next slide, please. So what is Gandalf? Gandalf is an end-to-end analysis service for the safe deployment in a large-scale system infrastructure. So Gandalf enables rapid and robust impact assessments of software rollouts to catch bad rollouts before they cause widespread outages. So Gandalf monitors and analyzes various fault signals. It will correlate each signal against all the ongoing rollouts using a spatial and temporal correlation algorithm. Next slide, please. So in a cloud scale system infrastructure like Microsoft Azure, various teams need to frequently make software changes in codes and configurations to deploy new features, fix existing bugs, and turn performance and so on. So with the sheer scale and the complexity of such infrastructure, even a small defect in updating one component may lead to widespread failures, which significantly customer impact, such as availability of the virtual machine service. So indeed, many catastrophes, service outages are caused by some small changes. Next slide, please. So each software change, therefore, must be rigorously reviewed and extensively tested. So even when a software change passed the testing, instead of updating all nodes at once, it is common practice to apply the change to production gradually, following a safe deployment policy. So from these two figures, we can see that more than 17% of the rollouts targets multiple clusters, and more than 20% of the rollouts last for over 1,000 minutes. Next slide, please. So here's the challenges we are facing for the traditional ways of dealing with this deployment. Component level watchdogs are insufficient in catching production issues that are meant locally but severe globally access clusters and regions. They may also miss latent issues such as memory leaks that happens hours after rollout. Additionally, a component level watchdog may fail to watch issues that raise only when interacting with other components. So at the same time, we also suffering from the false alarm. The false alarm, for example, mislead a local deployment health monitor and cause the innocent rollouts to be stopped, and also waste significant time and resources. So next slide, please. So here is the Gandalf and advantages of Gandalf compared to the traditional ways of dealing with this problem. So instead of analyzing each rollout separately based on the individual component logs, Gandalf actually takes a top-down approach to assess the impact of rollouts holistically. Gandalf continuously monitors a rich set of signals from the infrastructure telemetry data, including service level logs, performance counters, and process level events. So when a system anomaly is detected, Gandalf analysis if it is caused by a rollout. If a bad rollout is identified, Gandalf makes a no-go decision to stop it. So Gandalf also provides details supporting evidence and an interactive front end for the engineers to understand the issue and the root cause very easily.
The main idea of Gandalf is to provide an end-to-end analytics service for safe deployments and large-scale infrastructure on Azure. Gandalf derives its ideas of cloud deployments from safe deployments, which are from two previous strategies, which are known as blue-green deployments and canary deployments. Next slide. The first strategy I want to talk about is blue-green deployment strategy. The blue environment is known as the running production environment, which is typically your live environment, and entails a green environment, which is the newer environment with your updates from the software team. When your changes are ready and have gone through all the tests in your green environment, it'll be redirected to traffic into the new running environment, which will then be your blue environment. As shown in this picture below, the green environment is known as the pending deployment, as well as the blue environment, which is a live deployment. After the tests have been run by the software team from the green environment, it'll then redirect its traffic into the blue environment, which will now be your new production environment. The next type of deployment strategy is known as the canary deployment, which is typically a software rollout which releases an application or service incrementally to a subset of users. It could be in any type of increment that your company is looking for. So one example is to do it through 25%, 50%, and 75%. One example shown below is through a Facebook canary deployment with a small set of users having the latest software in the A2 region, while a majority of the users having it in the A3 region. So once the software has been tested out in increments, all the traffic will then be redirected into the A3 region. Next slide. Now we'll be discussing more about Gandalf under the hood. So as stated before, Gandalf provides an end-to-end continuous monitoring system for safe deployments. It has features in terms of assessment of rollout impact into a cluster and provides detailed analysis of whether a cloud deployment should be approved or stopped in terms of the rollout, and provides real-time features in terms of notifications to teams, as well as provides a root cause analysis of the investigation for any detection of anomalies. Next slide. The 4 layers of protection that Gandalf provides is to have a quality of control in a testing environment, safe deployment policies, and provide real-time alerts in terms of component level watchdog, and also provide any information gathered into the analytics service to essentially provide a monitoring feature. Next slide. Gandalf creators have determined through both experience and experiment that there are 4 types of failures that happen in a production environment. Few of them include hardware issues such as firmware glitches and incompatibilities, recurring software issues such as thread processing and race conditions, and hardware-induced issues such as power outages, disconnected or faulty network cable, and software outages due to bad code and buggy code as in system changes as well. Next slide. And now my teammate Mo will discuss the data sources from Gandalf.
What you see in front of you is the Gandalf system overview. We're going to go from data sources, where all the data is gathered, into detection, correlation, and decision engine, finally with the results orchestrator and the consumers in the end. What we're seeing here is the Gandalf system and how it's laid out in terms of processes. We're going to step through each process as we go along. So first are the data sources. Where does Gandalf get its data points from? It gets its data points from many things, but most importantly, task managers and monitors that monitor memory, CPUs usage, disk I/O, processes, threads, file handles, log files, etc. As you see on the screen, it gathers a lot of data about the entire machine. In addition to, it looks into logs. A lot of the stuff is done in Azure, so you'll see a lot of stuff about event logs. Event logs have all the information that's needed, and we'll see how Gandalf handles the event logs. So our first data sources are CPU, memory, disk I/O, process, threads, handles, and log files, mostly stuff that runs on the system. There are other data sources, but first let's talk about what a failure signal is. A failure signal is the subsystem reporting from an API or a DLL that says, hey, a failure has occurred. Now, Azure has determined that most failures happens in one of 2 planes. 2 planes or 2 paradigms of ideas. The first data plane or the first paradigm idea is the data plane. Those are components that are related to the VM infrastructure, the host, the operating system, software plugins, drivers, etc. The second is the control plane, which are components related to tenant level services, which are services provided for like Azure ARM, which is the Azure Resource Manager, which allows the tenant to create, update, delete VMs at will. The other part is the compute network and disk resource provider, the CRP, NRP, DRP, and they handle provisioning. So we got one plane, the data plane, which is basically about the VMs. And then we have control plane, which is how the VMs and stuff are delivered. All right, Gandalf's final data source are historical in nature. So Gandalf keeps historical data about module deployments, system configuration changes, etc. This data becomes very large after a while. We're going to see how Gandalf handles those. And how Gandalf handles this data is basically what they call the detection, correlation, and decision engines, which has two layers. The first is the Gandalf speed layer, and the second is the Gandalf batch layer. And we'll see how data is handled by both of those layers. Okay, so Gandalf's structure is in a Lambda architecture with two layers. The first is the speed layer. Now, the speed layer focuses on detecting simple, immediate issues that happen right away, and it provides quick feedback to developers. The second is the batch layer. Focuses on detecting latent or more complex issues that happen over a long period of time rather than a short period of time. This layer also provides more detailed evidence to developers because it is, like I said, latent and has a lot of time focused on it. Okay, so at the speed layer, Gandalf uses the fast pipeline, which uses Microsoft Custo. Custo is a column-oriented cloud storage that supports analytics, holds a few minutes of data, holds a few minutes of query data. You do query on your data, you get a little bit of data there. Has the custom query language based on data flow model, and cannot handle large volumes of data at the speed layer here. Only stores false signals that happen within an hour before or after each deployment. Very important. So Custo only holds the information for about an hour and then dumps it and then gets more information. So where does it dump it to? We're going to see that in the next slide. Okay. So here we run a lightweight analysis algorithm to provide rapid response. So here's what we call the emergency operations or emergency operator. He'll wave the flag and say, hey, something has happened. Azure historically has found that most catastrophic issues happen within an hour of the rollout. So this guy picks up a lot of errors that happen within that time frame. Now for the longer view, for the larger amounts of data, we use the batch layer, which gets data from Microsoft Cosmos. Now Cosmos is huge. It's made for receiving huge amounts of data. It's a Hadoop-like operating system, supports SQL-like query language, guaranteed single-digit millisecond response times with almost 99.999% availabilities with SLAs backing it, automatic and instant scalability, open source APIs for Mongo and Cassandra, fast writes and reads anywhere in the world with a turnkey data application and multiple region writes. It supports larger volumes of data, and that's the most important part. This part supports the historical data that the Custo cannot. This allows for Gandalf to analyze faults over a large period of time, and usually it's within 30 days. Okay, so the stream and batch analysis perform their thing periodically. The stream actually performs every 5 minutes and gets its information from Custo, and the batch processing that gets its information from Cosmos every 1 hour. The partial results from the analysis of each 5-minute and hourly is aggregated together and sent up to the analysis window to update the request orchestrator, which we're going to look at next. So this is the request orchestrator. We'll see that it's a web service and has two very large tables. So let's take a look at those. The results orchestrator of Gandalf is implemented in a highly scalable, reliable web service using Azure Service Fabric Framework because it's Microsoft. The rest of this, the results from the speed and the batch layers are stored in two separate tables in the web service. The results contain the deployment impact assessment, the recommendations whether go or no go, the anomaly patterns, and the correlation information. Okay, all that is then fed into the consumers. The consumers are the front end section of Gandalf, which consists of 5 sublayers: the monitoring front end, the diagnosis user interface, the REST API, the notification service, and the auto stop service. Gandalf provides a front end which does this. It enables real-time rollout monitoring and issue diagnosis supports. It allows for the use of rollout KPIs, rollout progress, node faults, container faults, allocation failures, etc. in real time. And after the decision of a rollout is made and sent to the corresponding team, Gandalf provides information to help developers investigate any issues and make a quick so that they can make a quick fix as needed. Gandalf then front end provides the following views: a binary decision page that summarizes all rollout decisions for different components and build versions in different environments, a rollout profile page that allows for the batch processing decision and associated diagnosing information, an issue profile page for bad rollout with diagnosis information and as the impacted clusters and trend in different environments, and a real-time tracking page that shows the rollout progress, related failures, etc. So how does Gandalf make its decision? It makes its decision using a correlation of 4 things: an anomaly detection, ensemble voting, spatial and temporal correlation, and time decay. So let's take a look at each of those things individually. The Gandalf algorithm consists of 3 steps. Anomaly detection detects the system level failures from raw telemetry data. That's all the data that's coming in from all the monitors. The correlation analysis identifies the components responsible for the detection of failures among the rollouts using ensemble voting, temporal correlation, spatial correlation, and exponential time delay. We'll look at those very carefully. The decision step then evaluates the impacted scope and decides whether or not a rollout should be stopped or not. So the raw telemetry that Gandalf analyzes, such as OS events, log messages, API calls, may be imprecise. For example, the usual HTTP response error 500 or error 404, which means file not found. That's very vague information. The 500 response says error, but what does that mean? Well, that's very vague. So what Gandalf attempts to do, the Gandalf process, the raw error messages and the errors are actually given what's called a fault signature. That fault signature is more unique and more expressive than the regular error message that you actually get. So after obtaining the fault signature, Gandalf detects anomalies based on the occurrences of the fault signature, not the error code, which makes sense because a lot of those error codes, if you're a programmer, you know, they're very vague. They don't tell you what's going on. Okay. Faults such as hardware and network glitches or power failures are common in large-scale cloud system environments, and there are many things that they can't explain, which they call cloud faults. We don't know what they are, but they happen. Simple threshold-based anomaly detection is ineffective because the system behaviors change over time, and because it's so large and there's so many components running, you can't find the fault in the big cloud. So Gandalf estimates the baseline from past data using the Holt-Winters forecasting to detect and to see and to better compare the impact of different fault signature. Gandalf calculates a z-score for each anomaly against the historical data that is correlated in process. So basically, when an event happens, Gandalf locks that event and gives it a score and determines what processes and what other functions were happening during that time. So let's go take a look at that, all right? So once anomalies are detected, Gandalf needs to correlate the observed failures with the deployment event and evaluate the impact of the failure on the fly. Note that the identified component within the error code might be the triggering component, but not necessarily the root cause. For example, a file that's gone, you get a 404, file not found. What causes that? Either somebody deleted the file, somebody moved the file, or the hard drive crashed and the system can't access the file, all right? So even though the web server says file not found, we don't know what exactly is the root cause of that file not found, right? So to identify the root cause, Gandalf uses ensemble voting, temporal correlation, spatial correlation, exponential time delay, time decay. So what is ensemble voting? So Gandalf uses vote-veto mechanism to establish a relationship between the faults and the rollout components. Votes and vetoes are calculated using the following order. Now follow here. For any event E, we call that event E, happens at timestamp F, we'll call that TF, right? On component C, at any time on the same node, there is a vote for veto or vote for. Now, a vote for says that all components deployed within the time frame, which is settable by the developer, which we'll see later, window size WB. So if an event happens, anything that occurs within the time frame WB before are voted to say, hey, they're suspect. Any event that happens or any rollout that happens after that, called WA, window after, are vetoed. And why is that? Because if an event happens, you're more than likely going to happen because something happened in the past or something is currently happening, not something is happening in the future. That's what WA is, it's the future. So an error can't occur because something happened in the future and it occurred now. That doesn't work. The logic isn't there. So once that's done, all votes are aligned and vetoes are summed up and aligned for component C across all nodes on the fault page, and they're summed up and the value is used to determine the fault. Now, after collecting and summarizing the faults of all the components, Gandalf then calculates the temporal correlation, sets the weight to temporal correlation, sets the weight values to each window, giving those that are closer to the time of the event more weight. Okay, what that means is any fault that happens at X time, anything that happens within seconds before or after, actually before, are said to be probable. Anything that happens after or way before are improbable. All right, so what we're saying is if a fault happens at point X, if an hour before or a day before point X, event G took place, and 2 days after point X, something else happens, those two events are not correlated with the event that the error at X time, right? Because they just not within the time frame of probability. So what that means is that any anomaly that happens closer to the time of the deployment will most likely be caused by the deployment than those furthest from the time from the deployment. Moving right along. Temporal correlation is then used to determine the spatial correlation, which is to say the confidence at which a specific deployment is to be blamed for a fault. So using the formula here, we see that SS, which is the spatial correlation, of E, which is our error, and C with our component, our error and component between time 1 and time 2, its probability is NF divided by NDF, where NF is the number of nodes with defaults during the deployment period T1 to T2. And NDF are present the total number of nodes with faults regardless of whether C was deployed during the same time period. That gives us a ratio. Now, if that ratio, which is B, if that ratio is less than or equal to our probability, then we don't use it. But if it is larger or equal to our probability, then that process is used for blame. All right. The confidence level, which can be set to 90, 99, it can be set lower if you want, is used for different sensitivities. Gandalf then identifies the blame component C by associating faults to the correspondent with the largest temporal correlation, which is to say that the average of all the correlations, the largest, is used to blame E event or fault. Okay, so the formula is the blame of E equals the average maximum of the temporal temporal correlation. Now, as time passes beyond that point, we're going to want to be, well, Gandalf uses a system where it's less and less likely that an event caused an error, right? And now how that happens, if the same fault signature appears again, the fault may still be blamed the old rollout if the fault page is between the old rollout and the fault signature is smaller within the same time frame. Gandalf needs to focus on new rollouts and gradually dampen the impact of the old rollouts, for newly observed faults are less likely to be triggered by the old rollout. Okay, so like I said again, if we have an event that happened at X time, the things that were happening right before X time more likely to cause than something in the future or something in the way past. So in order to achieve this, Gandalf applies an exponential time decay on the blaming algorithm, lowering the probability of the blame as time passes since the deployment. Now, the developers can affect that formula by adjusting the weights of the time frames. So Gandalf treats the input fault signals equally by default as 1. The developers can specify the importance of certain faults with customizable weights. The weights use relative range from 0 to 100, representing the least to most important. The default weight is 1, and weights are usually adjusted by developer reactively after investigating or reporting an issue. Okay, I will be followed by Beijing.
Okay, thank you, Maurice. So here we have the evaluation part. So first, let's see the business side. So from the number of the business side, the Gandalf currently monitors 19 component rollouts in the data plane, including host operation system updates, agent package updates, guest operation system updates, and so on. And it's also for 4 control plane component updates, includes a computer resource provider, disk resource provider, Azure front end, and the Fabric controller. The Gandalf system processing on average 217,000 platform events daily, and 770,000 events on peak days, and logs about 600 million API calls per day in the control plane. So including more than 2,000 fault types. The total data volume analysis is more than 20 terabytes per day. So Gandalf has significantly improved the release velocity. For each deployment, Gandalf can make decisions in about 5 minutes end-to-end on the speed layer, and it's about 3 hours in the bench layer. So next slide, please. So for the accuracy, almost all you can see is more than 99% of the suspicious rollouts are blocked before reaching production. The rest is blocked in the early stage of production. So this means Gandalf effectively limits the blast radius of most bad rollouts. So this figure shows the accuracy of the alerts in different environments. So we can see that most of the false alerts are issued in the stage and the canary environment, which is well aligned to the Gandalf designing goal. So the false positive rates in stage and the canary is higher compared to the algo environments because there are higher levels of noise feeder signals in this environment. Next slide, please. So here are 3 case studies. So first is about cross-component impact. In this case of deploying a computer resource provider service update, a Fabric controller least failure occurred. So first, the CRP team claimed that these failures were irrelevant to CRP rollout based on their past experience. After a deep investigation, it was confirmed that it was indeed a regression in CRP. So second case is about impact in specific region. Gandalf actually keeps monitoring the incompatible settings in a specific region. So for example, during one disk RP service deployment, Gandalf made a no-go decision in South France, which is a later stage production region. The alert turns out to be caused by a compatibility bug introduced by another component. So Gandalf detects not only immediate issues that happens right after the deployment, but also latent issues that happen several hours or even days after deployment. In third case, a operation system crashed during 24 hours after the deployment, and Gandalf issued an alert for them. Next slide, please. So here we provide a evaluation about the effectiveness of correlation algorithms. So first, let's take a look at the impact of the window size. So we can see from the figure that the choices of window size do not significantly affect precision. So this is because the main purpose of different windows is to differentiate the importance of the time between updates and anomalies. So as long as the window size can provide different widths to the time interval between false and update events, the precision should be similar. The window size has no effect on the recall due to the same reason. Next slide, please. So in this figure shows how wide adjustments impact Gandalf decisions on the control panel rollouts. We can see that the customizing WAS can significantly improve recall while remaining the high precision. In this, we're gonna be using a customizing WAS for the Gandalf. So next slide, please. So after all this evaluation and from the previous presentation, we could come to 3 conclusions at the end. The first, ensure bad rollouts are caught at the early stage is crucial for the cloud infrastructure deployment. So second, as the end-to-end analysis service like Gandalf is a practical solution to the cloud deployment. So the third one, an adaptive analysis model is very important for an analytic service like Gandalf. An ongoing optimized decision model is very important. Next slide, please. Okay, thank you very much for watching our presentation. And if you have any comments or you have any questions, you are welcome to contact us via Canvas or email. Thanks again.